Hello and welcome to Ask Echometer. My name is Carrie Ann Taylor, and along with myself from Echometer today, we have Gustavo Fernandez, who will be presenting. Also, Tony Podio and Lynn Rowland. We do have an Ask Echometer page that is accessible from our echometer.com homepage, and you can go there right now if you'd like and download the session 17. We're on session 17 now, PDF documentation bundle. And so that bundle contains a PDF of today's presentation, as well as the dynamometer features manual for TAM. And then right next to that PDF bundle link is a link to download the TAM examples that Gustavo is going to use to demonstrate the dynamometer analysis tools today. So also, if you don't already have the TAM software installed on your computer, you can download that from our website, and there's a link directly to the TAM 1.7 software from our homepage. So for today's session, Gustavo is going to give us a guided tour of the TAM software features for dynamometer analysis. So Gustavo, I'll go ahead and turn it over to you now.
Thank you, Carrie Ann. Well, yes, today we're going to be talking about how to navigate in the TAM software when you're analyzing the dynamometer data. Many users, unfortunately, don't realize that there are many features that they can use to better interpret the data and analyze it. So hopefully after today's presentation, you will be in better shape to go through the acquired data. One of the first things I want to highlight is, Karen, I think you mentioned that is we have all the presentations available in our website. Click on Ask Echometer. So in a couple of days, this presentation will be uploaded too. And there are several presentations so far along the year. Some of those talks about dynamometer sessions too, and in each of those sessions, we cover some examples, and that's also a good opportunity to see how to analyze the data and use the TAM features on the analysis. So sessions number 2, 6, 8, and 16 so far are talking about dynamometer data, and probably 2 of those will be very helpful or related to different features in the software, like number 6. They talk a lot about pump cut analysis on the pump displacement calculations, and also the session number 8, where a lot of reference load lines are used in the annotation button. So I would highly recommend you all to review those sessions if you haven't done it yet. For today's session, we're going to be using TAM 1.7.41, which is the last release available. We very soon are going to be launching the 1.8. It's going to be a release candidate, but it's going to be available really soon in the next days, if not weeks. Okay, there is one document that actually is available for all that you have TAM software installed, and that is a dynamometer features document. If you have your TAM software open, on the bottom left-hand side, you have a help button, and from there you can access to different documents and help you with how to acquire data, and also documents with more details like the dynamometer features. And a lot of the material covered today is going to be available in that document too. So that's available for all of you. This will be the main analysis window for dynamometer. And for today's sessions, we're not going to be talking about how to set up the sensors or set up the equipment, how to create a basewell file. We're just going to be focused on the dynamometer features available in the software. So on the upper part of the window, we have tabs with the different data sets that has been recorded, along with the dynamometer history. Also the test information, and we're going to be covering details on each of those. just after this. And on the lower part, then we have the different views that we have in the software, like a field view, details view, and different kind of views that we can explore to better analyze the data, depending on what type of data is being acquired along with the dynamometer. On the left-hand side, we have a drawing or schema with the surface and pump parts of the system, and that will help us to realize or visualize in real time how the polish rod is moving, how the plunger is moving in the pump, how if we have some tubing movement, also the opening and closing points of the up during the up and downstroke for the traveling and standing valve. So we can actually visualize how the pump is performing on the surface system is performing along the strokes. On the main portion of the screen, we have the dynamometer cards with the surface and downhole cards. And there are a couple of ways to visualize this. I'm usually plotting both surface and downhole card in the same plot to help me to visualize. And we have examples that let you know when it's even more necessary to have both dynamometer cards plot in the same chart. On the right hand side, on the lower part, we have annotation button and pump car analysis. And inside those two buttons, we have different features that will help to fine-tune the analysis or plot some reference lines in the dynamometer chart. And we're going to be discussing every of these buttons in more detail. And this is kind of explanation. So let's start with the upper part of the screen. So we have dynamometer test tabs, and they are arranged by time. So all the dynamometer history is going to be available on the very top of the screen. It's going to be easy to toggle from one data set to another just by clicking on the upper portion of the screen. And all this data will be related to the well name that's plotted right here in the just above the wellbore schematic. I'm going to be switching a lot between the presentation and the software. Like this is one example where we can just switch from one measurement to another just by clicking on the date and time of each dynamometer set. So the next will be talking about the dynamometer history. Like along the time, you will be recording more and more data for the wells. And like right now, if I click on the dynamometer history, we'll have a plot or a table shown with all the dynamometer data, and you have the options to show just the date and time or the thumbnails of the surface and downhole card as a quick reference, but plus certain information that you can actually customize on what information do you show on this history of dynamometers. And right now I have all the options selected, so you can once you have this, is also a good way to print kind of a dynamometer report. So it will allow you to, from the PDF button, to create a PDF file showing the dynamometer report. Let's do that real quick. So if we click on DYN history, it will give us a table. And as you can see on this well, we have several dynamometer data. I'm going to be using this one here, but you can toggle or select any other dynamometer data. Once you select, the software will automatically show the data related to that date and time. And you can also show the thumbnails. So if you need to print a report for the dynamometer's performance in a specific well, just click on the PDF and you can save it in somewhere in your computer, and you will have a PDF report printed for all the dynamometer data related to that well. Let's keep going. And the next part is the test information. You might be familiar with this, and when you click on the test information, you can do that, and the software will show the version that was used to acquire the data. In my case, was used TAM 1.7.41, and also what sensors were used for that dynamometer set. In this case, we had a wireless horseshoe load cell and we had a wireless pressure transducer and a wireless power probe. And we can find details on each of those sensors by clicking on the detail button. Like for example, if you can focus on the wireless pressure transducer information, and that's a serial number for that pressure transducer. That's acquisition rate, which is, it may be modified. The software by default will acquire data at 60 hertz, but you can increase the sample speed based on your needs. Like if you have a pump tagging down, for example, and you're missing how hard is this pump tagging, and then you can increase the sample rate. That's one of the examples when you want to increase the sample rate. You can also see the coefficients in that pressure transducer and the temperature and the offset, when was it performed. So we can compare the last offset for this pressure transducer was on March the 12th, and that matches with that same acquisition date. So it was zeroed the same day. And you can do the same with the rest of the sensors. Also, you have a field to input relevant comments on that specific test that may be useful when you're analyzing the data. So all the sensors information can also be quickly viewed when you locate your mouse pointer on top of the icon of that sensor, like this one here. Let me go to the same dynamometer data set. So if you locate your sensor, you will have, this is a power probe information, this is a PRT information for those specific sensors. So the next portion of that will be exploring the different options that we have on the dynamometer plot. As I mentioned before, we can plot this together, or we can plot the surface and downhole curve separately. And the dynamometer plot, we have some options, and there is a button that I cannot display on the presentation, but I will do it in the software. Like there is a red dot that you can position at some point in the stroke, and it will give you what's the load associated to that point, and also the stroke length. One more option is you can actually lock this dot. If you're trying to focus on a specific point, you can keep it there and print the report and take a picture of this image. You will be making a reference to a specific point in the plot. There are several lines also in the plot that we'll review on the annotations button later on. But let's keep going. One more thing that you can do on the plot itself is options to play with the data. So you can do a right mouse click on the dynamometer card, and it will allow you to either print the image, copy that to a clipboard, copy the data, not as an image, but the data itself to a clipboard, export the data so you can use it like in an Excel file. There will be also an option for exporting the DYN file, which is kind of the default of the industry standard for dynamometer files if you want to export it. And we can also add a note, like if you want to focus on a specific point in the plot, you can, just switching back to the software, let's say you want to point somewhere, and you just locate your mouse pointer, do a right mouse click at some specific point, you add a note. And you can say TV opening. And that's your note, and you can locate it differently and relocate the comment wherever you want. That's also a useful feature, and that will be, if you copy the image or you print the report, that will be included. Moving on, let's explore the different views that we have when we are analyzing a dynamometer data. So the first one would be the field view. And the field view, in the upper part of the stroke, we have the total length of the test. Then we also have the number of strokes recorded and the average speed along the test. So this 8.37 is related to the total length of the test, but on the right-hand side, we have 8.39, which is related to this specific stroke. Here we'll also have the effective plunger travel. EPT stands for effective plunger travel, and that's a relationship between this dashed line for the opening point of the traveling valve and the maximum plunger travel. So that's 71%, and we call that 71% fillage in the pump if we are locating correctly the opening point of the traveling valve. We also have the pump displacement calculated based on the effective plunger travel. So the software will use this opening point of the traveling valve for calculating the pump displacement. We also have the pump displacement calculated based on the maximum plunger travel. That's assuming the pump would be full. But that's theoretical because that do not include any adjustment or correction. And we're going to visit briefly that later on. The software will just do a simple calculation for a full pump and a simple calculation for the pump fillage displacement at this point, not accounting for different variables that we're going to explore later on. So the next view will be the detailed view. On the detailed view, we have a different kind of information. So on the upper part, it has changed. Now it's showing the peak and minimum polish rod load and pump load. And the peak and minimum polish rod load will be the upper point and the lowest point in the surface car, and the same for the pump will be the upper and the lowest point in the car, but also shows the power, how much power is being consumed or applied in the polish rod and also at the pump, and that's calculated based on the dynamometer card area. On the right hand side, we have a series of values that some of those are going to be covering more details on the annotations and the pump car analysis, like the pump displacement. There are some adjustments applied on the pump displacement. And one thing that you can notice is the pump displacement adjusted is much lower than the one shown at the field view. And we'll see what is the software considering to get to this value later on. Also, there are some sessions that you can review, like session number 6 is a good one. Yeah, that talks a lot about TAM considerations to calculate or adjust the pump displacement. Okay. Another value that we can focus on is the FO max, or the calculated fluid load. The maximum fluid loads in the system. So this will be considering that we have no help from the well, assuming like we have no pump intake pressure. So the pump is actually lifting all the fluid loads. That has to do with how much pump discharge pressure we have in the system and the plunger area. So we have the pump discharge pressure will be the tubing pressure plus the pump intake depth times the fluid in the tubing gradient. And so we multiply that for the plunger area, and these are the values for this specific example. And you can do this, you can try this with your specific well. That's 4.27, 4,270 pounds for this well. The next value will be the system efficiency, and that will be considering the power at the polish rod, which is 7.4 on this one, and the average power or net input power in the system. And we also have the motor to pump efficiency, which will be considering the power at the pump from the downhole car and times the same the average power being consumed. The next value is the pump intake pressure. It's important to highlight that the pump intake pressure shown in this field is a pump intake pressure calculated based on the dynamometer measurement. It's not a pump intake pressure from the fluid level, which can also be used as a reference on the dynamometer card to see if our dynamometer height is kind of matching with what is supposed to be based on the fluid level information. But this one here is considering the pump discharge pressure and the fluid load for that specific pump. So the fluid load value will be revised quickly later on the pump car analysis. But again, this is a pump intake pressure calculated based on the dynamometer information. Other two values are the damping factors, and those damping factors will be, and here will be revised on when do you need to alter or manipulate the damping factors under some specific conditions like high friction wells, based on either highly deviated wells or due to high viscous oil or something like that. So rarely you will need actually to adjust the damping factor, because unless you see you have the need to, and we have a couple of examples to show that. The next value will be the tubing pressure. And the tubing pressure, we have a couple of options. Like regularly, if you're not using a tubing pressure transducer, like a wireless pressure transducer, in this case, we had a wireless pressure transducer in the tubing, so we have that information that will be, the software will estimate the average for the tubing pressure during that specific stroke, and we will show that in a minute. But if you're not using that, you will need to enter the tubing pressure. So I'm going to jump into the software right now, and I need to select the same dynamometer card. So I will use this table to quickly go to my measurement. So I know we were using the 50K wireless horseshoe load cell, and with the pressure transducer. So the pressure name will be a WPT 107, so I can quickly go there. And we revise some options to do a right mouse click and copy the data to a clipboard. So I will copy the data, and I'm copying the data related to this chart. And now I will go to an Excel file and we'll paste the data. We're pasting here surface car information, that's a position and load, and that we're also plotting position and load for the downhole car or the pump car, but we also are plotting the pressure along that stroke. So if we go and calculate an average for that pressure, that would be 57.4 psi. And let me make this a little bit bigger so you can see the number better. So 57.4 psi is the tubing pressure, and I think I missed that. Okay, go back to the presentation right here. So that's where that 57.4 comes from. So the next view that we have is the chamber pressure. And here the software shows the load of the pump car, and it also shows the plunger position, and it's related to the pressure in the chamber. And this pressure in the chamber will be here, and the red point is going to be, we can activate or not the chamber pressure being plotted. And at this specific point, we have 1400 psi, and that's pretty much what's showing here. And let me go to software again, and I will go to from details. That's 57.4 we were mentioning, and now go to the chamber pressure. Now we have this red dot, and we can see how the plunger is moving in relation to the pressure. So the plunger actually is moving down, and is now the pressure decreases, and it decreases a good amount of pressure, like almost to zero, and the plunger is not moving that much. If you look at this plunger movement, and we're just showing the pump section here in the plot, then at some point the loads are peaked when the throttling valve closes. The loads are peaked, and then the compression zone during the downstroke, we see how we don't need so many inches, so the pressure decreases or drop really quick. The next tab will be the power torque, and again there are, for more details on the power analysis, we have another class or session, I think it's number 12, for torque analysis. So on this plot, the software is showing two values in the chart. which is the measured torque, which is the red line, and we can see some out of balance unit here, the upstroke compared to the downstroke. This is kind of a weight heavy pumping unit, but we also have the balanced torque plot or in the chart. And the lower area here, we can see that below the torque being below zero, and we can compare that to the power analysis. On the right hand side, we have the peak torque during the upstroke, 213, the peak torque during the downstroke, 277, and the balance torque that would be for the 245. And the software also have the recommendation how to balance the unit. So if we have input the correct pumping unit, crank information, counterweight information, and the software can give us a recommendation on how to move those counterweights in order to achieve the balance condition for that specific assuming that stroke selected represents the normal pumping condition in the well. So when we click on the power gearbox torque calculator, we have this window, and probably you need to focus on how to move the counterweight in order to balance the unit. So that you need to move this counterweight 6.5 inches in, which means towards the gearbox shaft, in order to balance the unit. But again, we have a full session with more details on pumping unit torque. That the intention of this presentation is to show you where the information is accessible. Okay, the next view would be the power analysis. And of course, this window will be available when you perform power analysis, or you're using a power probe, so in order to collect power from the system. There are two plots here. One is the power in kW, and we can see here how the stroke, the power is distributed along the stroke, and we can see the power goes below zero where the motor goes from consuming to generating energy. And we can see that current being consumed along the stroke, and this is matching with what we saw in the power torque window. So we have more power consumption, more current consumption during the downstroke compared to the upstroke. On the right hand side of the screen, we have the runtime, we have the rated current consumption, but we also have the monthly electrical bill. How much would you be paying for electricity, assuming that this dynamometer car actually represents the normal pumping condition of this well. This is the motor rating, the recommended minimum size for an IMAD motor, and the system efficiency. The next window is, or next view would be the analysis plot view. And this may vary significantly based on what kind of analysis you're trying to perform in that specific well, what kind of answers you're looking for. It's very customizable, and we have actually two plots to relate the dynamometer information. We have on the sides of each plot, we have options to select from a variety of data. Of course, that will be more or less depending on what kind of test you have performed. We performed the power test, so also the power options will be available. But you can actually select from a wide number of options. So the next thing that we can consider is that if, like in this case, you have plotted polish rod load compared to the plunger position, polish rod position to plunger position. So if both sides have the same unit, you can combine those left and right axes to a single axis. So you can easier to read that. And we have some examples to show this better. On the other hand, you have the options to compare that data or plot the data against, like this. At this point, we have a plunger velocity. You can plot the plunger velocity against the crank angle, plunger position, or polish rod position. If you're focusing on one single chart, you can expand the view of that chart, and as almost any other unit in the TAM software, the units can be changed. Even for this plot, you can change the unit from seconds to minute to clock time, and let's go there and do that. So if we're in the detail view, we have different plots here, and this one is also polish rod against plunger position. We can combine that, and we can change this right now in clock. I usually have it in seconds, so I know how long a stroke lasts. But again, you can change the units not only here but in many places in the TAM software. Okay, let's keep going. Raw data. The raw data is actually available when you're analyzing the data, but it's also available in real time. So you have access when you're acquiring the data to see how the loads and the acceleration, and depending on what type of sensor you're using, how the values are changing along the test. So you have a raw data access in real time when you're performing the test, and also when you're analyzing the data. So here on this screen, you will have either a section, or you can expand the white area here to observe the whole trace or dynamometer session. And on the top, you will always have the load calculated or measured, either with a PRT or a load cell. And on the bottom chart, it will change a lot based on what kind of sensors you acquire. Basically, you at least will have acceleration, position, and velocity if you're just acquiring dynamometer data. But if you're using a pressure transducer, you will have the pressure available. If you're doing power measurement, you will have the power, current, and voltage, like we're doing in this specific well or example. Once you're here, if you want to focus on some portion of the trace or the data, you can use these buttons to navigate in the data, and you can also, from the raw data, you can access to the valve test, and that's the next thing. Before going there, let's see how we navigate in the raw data. So on the top of the screen, you have, actually on both of them, you have a chart which shows the full dynamometer data set, and you can adjust this to explore different portions of the trace from the very beginning. And we started recording, and the unit was down, then we started the unit, and you can see how the current behaves at different point. Like this here, we're doing a valve test, and the pump was stopped and started, and we can see the peaks for that power consumption, and you can see how the power also behaves, or the voltage drops when the current goes up, and so you can actually see the raw data, how it is collected. But also from the raw data, you can access the valve test if you have performed the valve test. And this is probably one of the major advances in TAM, when the workflow is changed by when you're using TAM instead of TWN, because TAM has the capability of recognize. He's smart enough to know if you're performing a valve test, so you don't need to interact with the software. You just go straight and recording a dynamometer data and stop the unit to do a valve test. You don't need to stop the dynamometer session and start a new valve test as you were, if you are an old user, as you were doing it with the TWN software. So in TAM software, it's just, as you can see here, I'm going to show this again. So we're recording dynamometer data, not stopping there, and then stopping the unit for the valve test, traveling valve, 2 standing valves, and 1 more traveling valve test, and then continue recording data. All that is in the same data set, so you don't need to actually stop and record a separate valve test. So from the raw data, we can first visualize the valve test, and if we double click in here, the software will switch into the valve test analysis mode. And coming back here, just double clicking here, we have some options. And this is the data assigned to the valve test analysis. So we need to, if we want to perform the valve test analysis, we need to activate either the traveling or the standing or both valve analysis, either by checking the box or clicking on enable valve analysis. It will turn on those capabilities. And the software will show, like at the beginning of this traveling valve section, this is the yellow area, which we can move and drag. I will show you in a minute. Will be the measure load, and the beginning of the standing valve will be the measure load, and you can alter it or change that, and then later on relocate it. So I'm going to turn on or enable the traveling and standing valve test, and that's the software default. So the software will automatically select that, and you can change it just by dragging this portion or by moving how wide or thick you want this traveling valve analysis section. So the software will calculate the leakage based on the load drop and other variables, the tubing, elasticity, but that's another topic. We're not going deep today in there. Okay, so going further, we have a next option in the raw data when the data analysis or the stroke analysis can be reprocessed. So we can actually click again and reprocess the data. And right now I'm showing an example here where the software wasn't able to find any strokes. If we look at here, we have 0 strokes, even though we can see the loads are fluctuating up and down. So we're having strokes here. And we run this test for almost 10 minutes. So we know we're having strokes, but the acceleration, if you look at here, acceleration is really close to 1, so it's not changing much. This is typical normally for a slow pumping unit, so it's very, very low strokes per minute. So if this is the case, we can try to reprocess the data in order to help the software to use a different method to try to calculate the velocity and the position in order to get the stroke calculation. So when we click on process, we have options here to change the filter width, or the filter type, and also change the acceleration integration method, which is what the software uses to estimate or to calculate the velocity and the position of the polish rod. And putting that together with the loads, then we have the dynamometer car plot. So on this specific well, we needed to change from the TAM default method and the moving average filter with 0.5 seconds wide, which is the default in the software, to the histogram. When we click on reprocess, on this condition, the software will ask you if you really want to proceed, as any changes, if you were working on a dynamometer car, any changes that you have performed so far will be lost when you reprocess the data. I don't have any stroke anywhere, I will say yes. And now the software, we can see now that we have gray lines with numbers on it, and between gray lines, that will be 1 stroke. So from 3 to 4 is 1 stroke, and that matches with this acceleration data. And the software was now able to do a proper calculation of the acceleration and getting dynamometer data, and we went from no pump cards calculated to 22 pump cards. And this is the average strokes per minute in this well. So this is very low speed, 2.64, and I have another couple of more examples with less than, I think it's 1.3 strokes only. So it's really, really bad for the acceleration. Okay, the next thing that I want to talk about is events. And this is a very nice features that we can, let's say, play a lot with the data. And when we click on event, first we have options also to plot or to show different strokes on a list. But if we click on event, we will have this chart. And these are thumbnails of the dynamometer cards. It's very useful. We can quickly review how the dyno card shapes if we scroll this, and this is the portion of the tray of the dynamometer data which shows the valve test. But we can drag this from this bar to this point, for example, and there's one dyno card highlighted in green, and that's a 57, which is exactly the pump card we're showing right now, the stroke 57. So that will be highlighted in green, but I also can keep dragging to the left, like if I take this and drag it here, I can see how the first, let's say, 26, 27 cars were full pump, and then from that point on, the fluid pound appears. So that's really common when you stop the unit and take some minutes to install the dynamometer, then start the unit and start recording right away. And the fluid level has a chance to rise. So you have enough pump submergency and pump intake pressure on the first strokes to have full pump, and then the normal pumping condition appears. But let's say you want to focus on this area. So we can, by using the mouse pointer on your keyboard, you can select the first, let's say the dynamometer car point 20, number 26, 25, and push your shift key on your keyboard and clicking on 34. So that will give you a highlight of those dyno cards, and what will happen in the plot is we'll have here all those 10 dynamometer cards overlaid. We can see from full cards to fluid pound, and I can do that real quick in the software. If I go back to raw data and I select one dynamometer card, doesn't matter which one it is, I'm going to the field view. It's important that in order to be the overlay, you need to be in the field view. That will not happen on details, because the details view will be an analysis for that specific stroke. So being on details view, coming to events, and I said like dynamometer card, this is still pumped off, and there's fluid pound appears. So from 25, let's say, to 32. And you can do this, and that will be overlaid. That's easy to do. But you also can do something different. You can, let's say, well, before going there, we have to notice that when we select overlay multiple dyno cards, the software will now change from a specific stroke per minute for that stroke to show the average for the highlighted or overlaid card. So this is the average stroke per minute, and all the values of pump fillage and pump displacement will be related to an average for the cards selected. So like at this point, and this will be useful in just a minute. I will show you how to do that. You can also overlay independent cards, like you want to overlay the cards 25 and 35, because those are the full pump and the pumped off card, and you can do that by clicking on them. If you have a one dyno card that's your reference and you want to overlay that card with different cards, you can lock one dyno card. You should do a right mouse click and lock the card, and then you click on different ones. So let me go there and do that. So let's say I want to always have in the background the 25, I lock the card, and then start comparing. This is plotting two dynamometer cards at a time while I'm clicking here. So I see it's appearing the fluid pound even more, and that will be locked. I'm going to unlock and have this section overlaid. If you put your mouse pointer, you will see how there is a green line selecting or showing the dynamometer card on the bottom. I will be moving, and you see how the dynamometer card highlighted in green will change, because that's the one that I'm pointing with the mouse. Okay, when is that useful? Like on this well, we have 97 dyno cards. So which dyno card is the one that I'm going to print for the report? And there's when selecting multiple cards and trying to get an average becomes useful, because like this was the very beginning after the well was stopped a few minutes when you were installing the dynamometer sensor. So this very likely is not the average behavior of this well. So I better look forward. So 20 strokes, almost 30 strokes later on, the software is already showing kind of a more consistent dyno card. And from this point all the way down, just right before I stop the unit, because again, once I stop the unit, the next card will be a full, almost a full pump. So I don't want to get the full pump card. So I would better stay on the what looks like a more normal behavior on this well. So I will go back and I will highlight like from this point there. And we have all these dynamometer cards, and from 32, which is a fluid pound condition, to a 71, we have a 71% fillage. So the average for what looks to be the normal condition is 71% fillage, and 8.39 strokes per minute is the average there. So I have check the data and I see stroke number 57 has the average fillage and the average speed. So I'm confident that stroke 57 is a good representation of the normal pumping condition. I could select also 52, which also had the 71%. So there are, I'm going to stick with the 57, which also has the speed that I saw as an average. Okay, let me keep going. The next button that I want to show is the replay button. That replay button displays the replay controls for viewing in real time what was recorded. So the pump stroke will be shown as if they were in real time when they were originally recorded at the well. So for this one, we will click on replay, and if we want to focus, like I want to see how the dyno cars looked, or make a movie of how dyno cars look when went to from full pump to fluid pump condition. And I'm just getting this as an example. You can use the videos to explain different phenomena in the well, and many times it's much easier to explain something that you can see. So I'm much more a visual guy, so I really like this feature in the software. And you can customize what you want to show. So like I'm putting here from 27 to 31, and the software will actually make a movie or show you like a movie in real time, how that looked when it was recorded. And you can also click on make a movie, and the software will create a MP4 video file, and you can save it in your computer, and then you can play it. So let's do that real quick from the software. So we were wanting to show from full pump to fluid pump condition. So I'm going to plot from stroke 27 to 31. That's what I want to show. So I will click on reply, and I will modify the stroke length, because if I click on play, I will start plotting or displaying from stroke number 1 to 97. So I will change that from 27 to 31, and I click on update, and the software now updates the film of the plot right there. I'll click on play, and you will be able to see how the polish rod and the plunger moves like this was in real time at the well. But you can also slow down or increase the speed of the video. Once you're satisfied with that, you can actually make a movie of it, and the software will show a red line where the portion of the stroke that is being shown right now. If we click on make a movie, we'll just save it somewhere in my computer. So it's doing a movie from cards 27 to 31. So the next slide would be annotations. And in annotations, we have several options to plot on the chart. And again, they were further discussed in a different session. I have some material here that I can show you. So like this one here will be usually I plot, as you saw, surface and pump card in one plot, and we'll see some examples on how or why. You also saw the power slide. I think I didn't talk about it, and I will bring the software again here, and I will again select the dynamometer session that I was showing, and that was card 57. So I'm going to go to 57 right here. So that's the same dynamometer card that we were plotting. And if we click on annotations, and in annotations, I have two screens, so I might be dragging some things in here. In annotation, we have some checkbox that we can either plot or not. And like this well here, we can plot an anchor or tune stretch, and you see how the line disappears or appears in the plot based on your selecting or not. And the tubing stretch, or you can also plot the rod tubing stretch on the surface car, and depending on the analysis you're performing, this may or may not be useful for you. Something that we usually plot is FO max line and the FO from the fluid level, and they should be kind of this well is matching pretty well the dynamometer car shape or height with the fluid level or FO fluid loads calculated from the fluid level. So this is that car here, and there are several others that we can plot. Always we like to show the valve open and close points because sometimes the opening travel valve point is not properly selected, so you want to intervene there and drag the point. You can drag it and just click in there and drag it to the right place, like I'm doing it right now. And there are several others. So in the presentation, there are left and right hand side. You can show in the left hand, you can show the pump intake pressure or the pressure in the chamber. So there are several values that we can plot in here. Oops. Like the pump discharge pressure, you can see it in the plot. You can enable or disable that. You can show the pump intake pressure. I decided to show it all the time from the liquid level. And the line for the effective and maximum plunger travel, that usually I display those two. There is a blue line here for the gas-free fillage line, and there's again another session that discusses further on how the software calculates that. Anyway, you have here more details on all the options on the left-hand side that you can see here. Another slide for the options on the right-hand side if you want more details. But aside that, in the annotations, the software can also allows you to select to which liquid level is that dynamometer data set associated. So we saw we have a pump intake pressure calculated from the fluid level, and we use that information to plot in the dynamometer car. And the software allows you to select from which of the fluid level shots in that well you want to use to work together with this dynamometer set. So you can change if you want to. Normally the software selects the fluid level that is closest to that dynamometer set, like this is the March the 12th at 4:21, and this fluid level selected by default in the software is the same day, 9 minutes after that dynamometer set. So the software will try to match the closest liquid level. But let's say you have that specific day you don't have a fluid level, but you have a fluid level that's representative from a couple of days ago, you can use that. Or a fluid level that was not representative because you stop the unit and the fluid level rise because it's a high producer well. So you don't want to use that new fluid level. And then you can actually change that. But also the software allows you to select to which valve test you want to associate that dynamometer car analysis. And of course, if this dynamometer data set has a valve test, you want to use that, but probably that valve test was bad. It wasn't right. But you have another valve test, and because you didn't apply the brakes in the right point, or if something happened during the valve test, they don't want to consider that, then you want to change it. You can do that too. One more thing is, of course, you want to be sure that the valve, which options you have with valve tests, which dynamometer data sets includes valve tests or not. One more thing is previous strokes. We have already seen how to overlay different strokes from the same day, from the same data set. And we've shown that in this slide here. So we know how to select multiple dynamometer cards for that specific plot. But the software also allows you to overlay strokes from previous measurements. Actually, when you click on previous strokes, the software shows you a chart that's pretty much the dynamometer history with all the options that you have to overlay. So you can actually overlay from any other dynamometer recording that you have. So let's say we want to focus on two different strokes, and we will keep on the background in black the current dynamometer card, and we will have colors for the new overlaid cards from different dates if you want to. So we're right now comparing dynamometer cards from different dates. Okay, that's over there. And again, the black one will be the current card associated to this date and time, and then you can pick from the table. And you have a maximum to overlay of 5 dynamometer cards, and I think over that would be too confusing. Okay, now let's go to pump card analysis. And again, in pump card analysis, we have a lot of information to review, and the intention of this presentation is just to show you where the information is accessible and not to go into the very deep details. So on pump card analysis, we have the first tab will be a damping factor. And then I will show you how the damping factor works and how it affects the dynamometer card shape, but the user can change the damping factor during the ups or the downstroke, and this will affect how the wave equation models the downhole card or the calculation. And once you move it, the software will adjust the calculation of the dyno card or how the dyno card looks based on the damping factor that was modified. So a new value can be either entered, or you can drag the slider here to a higher or lower value of damping factor and the upstroke or downstroke, or you can move both at a time by locking the sliders. And that will change the dyno card shape because you're affecting how the wave equation is calculating the downhole card. And this is kind of the explanation of that. The DRAMP. The DRAMP option is actually it's a new option in TAM. When I say new in TAM, it's because it wasn't in TWM. And this tool can help the user when they have dynamometer data, usually when collected with a PRT. The PRT is affected by a bent polish rod or a misaligned pumping unit. So we have a slant dynamometer card, either tilted up or down, and the software will make a correction. I have a very good example for you on that after the presentation. Correcting a dynamometer card that was acquired in a bent polish rod with a PRT. It works pretty well. The tubing gradient, we have several options, and the user can actually either select from the gas-free, from the well test information that we input in the software. So this is basically a tubing fluid gradient with no gas in it. So if the well is producing gas, the more the gas is produced, well, not the well producing gas. If the gas is getting into the pump, because the well may be producing gas, but the gas may be flowing up the annulus when you have the pumping tape below the perforations. But let's say the pump is actually producing gas. So we know we have some gas flowing up in the rod tubing annulus. So this tubing gradient is not appropriate, as this is related to only fluid. Then we have the gradient measure from the valve test. If we perform a valve test, this option will be available. And if it's a vertical well, not much mechanical friction in the well, this may be representative. But for deviated well or viscous oil, where you have high friction in the system, the valve tests are not that good to estimate the tubing gradient. There is another option with using multi-phase flow correlations, and my understanding is for low water cuts it works really well, but high water cuts doesn't work that good. Or the user can actually enter what's a tubing gradient in the system. So the software will use either of these values to estimate the pump discharge pressure and make some different kind of calculations in the system. The next tab is the pump intake pressure. The pump intake pressure actually is calculated. That 88 pounds that we saw at the first slides, it comes from the calculation here, where part of that equation involves the fluid loss. This FO here, the FO will be the the load difference in the pump car on the upstroke and the downstroke. And the software by default selects the average upstroke loads and the zero loads during the downstroke, and based on that difference, that will be 4116 pounds, and that will be in this formula together with the fluid gradient that we discussed in the previous tab, along with the input in the software like the tubing pressure, the pump intake depth and TVD, and the plunger size to estimate the pump intake pressure. This is kind of the explanation. And the last tab would be the pump displacement. And there are several considerations that the software may or may not do if you select them to estimate an adjusted pump displacement. Either it can adjust for gas-free in the pump, anchored or unanchored tubing, can adjust for slippage, and there is an equation here we can show for the slippage that was also discussed in previous sessions. But if you uncheck, let's say you uncheck the adjust the pump displacement for slippage, this will be grayed out. So let's do that in the software. I will click on pump car analysis, and I'll go to pump displacement. You see the values are kind of in black color. There is, if I click here to unselect this pump displacement for the slippage, then this value will be grayed out, and that will represent this value is not being accounted. So we're saying that the pump has no slippage at all. And of course, the more accurate that value is, it depends on how good the input is. So the software will have like 3,007 for the pump clearance, which is one of the values considered in the equation. And you need to adjust the pump information, like having the right pump plunger length and having the right pump clearance, and you can get those pump details from the manufacturer. And also the fluid being produced, you need to have the viscosity of that fluid. So even though the software will attempt to do pump slippage calculation based on your input. Okay, let me go back to the presentation. And like here, I was looking at this 118. That's the same value shown in the second view, which is the detailed view in the software. This 118 barrels per day matches with the calculation on the pump displacement tab. There are other values for adjustment to standard conditions or conditions at the tank that it can be reviewed as well. Okay, so once you have the dynamometer car selected, and we said the 57 is the average car, and we have the analysis done, and it's matching, it's okay, and you're good with that, you can proceed to do a report. So once you have that, you click on report, and the dynamometer report may show different type of information based on what you acquired. Like in this option, we have the main window, the main page will be the dynamometer report, which includes gearbox torque analysis, the surface and downhill car, rod loading analysis, what the pump information is, and not only that, but how much was the pump stroke, what was a gas-free pump stroke, and information related to the pump. Also production information, system efficiencies, and it relates all that information to one flow level. That's important that you select the correct or the representative flow level to that report. So the pump unit information, stroke length, speed, and peak and minimum polish rod load, and power at the polish rod. Tubing and casing pressure is being shown as well, but you can also have a second page for the torque. So you can either activate or not these pages. This is the torque plot, which has the mechanical torque calculated and also the power torque calculated. And this is a very good approximation. You see how similar the calculations are from the power data and the counterbalance information in the well. Like if you input the crank and counterweights, this plot should be correct on the right pumping unit. And also the balanced torque. We have here the gearbox loads plotted on the dynamometer car, and pump unit information to see how in balance it is or out of balance, and also recommendations to balance the pumping unit. So all that kind of information will be available in the total report. We have the power report. So if you acquire power data using the power probes, you will have the power torque and the power analysis with different kind of information, including your calculation for electrical bill and how much power you're using in that in the system. Yeah, different kind of information. And the analysis plot will be exactly as you left it in the analysis. So when you were analyzing the analysis plot, and different variables you plotted there, where you selected or you located the cursor or the dash line, that would be exactly in the report. Something that I should mention when we're overlaying different dynamometers is the dynamometer card that is being overlaid corresponded to the last dynamometer card that you analyzed in the well. So like, let me go back there for a second. Just recapping that. So like in this example, we overlaid one dyno card from this date, but we probably had 100 dyno cards from that day. So which one is being plotted is the last dyno card that you analyzed. So where you left the software or you left the well and you jump to another well. And once you have the pages in the report that you wanted to report, and then you can also have some settings where you can change or input your company logo in the report. If you're printing, you can put a footer with your company information too. If you're printing a Word report, you can do also a Word report. You can put more comments in there, and you can paste that in here. But once you're done, you can actually either print that and send that to a printer. That's a regular printing, or you can print that as a PDF document. Or if you have the email software updated in your computer, you can click on email, and the software will automatically attach that dynamometer report in your Outlook email. And I think that's all for the presentation. Before we jump into the examples, I would like to know if we have some questions.
Thank
and
you,
Dr.
Gustavo.
Florian Roland here. Thank you.
Excellent. We do have a couple of questions and comments. The first question is from Riley, and Riley is asking, can you discuss what FO max is just a little more?
Yes, okay, let me find the slide for the FO max. So one of the values that we were discussing is the FO max. And the FO max line is, you can plot it in the system. You can go to Annotations and be sure that you have the FO max line here. If I will be clicking to see, now it appears here, FO max is 4.27, so which is 4,270 pounds. What the FO max means is that's the maximum fluid load that the pump may lift, assuming that we have no pumping type pressure, like we have no pump submergency. And that assumption takes us to have all the liquid column is being lifted by the pump. So all the liquid column have a hydrostatic pressure on top of the pump. That's a pump discharge pressure. So that's a hydrostatic pressure plus the tubing pressure. And that across that pressure is being applied on the pump plunger. So on the presentation, we have a quick equation that shows the pump discharge pressure calculation, which is the one here in the brackets, and THP, and then the plunger area, because that pressure is applied on the plunger. So if you open any of your wells and you can input the right data, and remember this is plunger area, not diameter, so that will be square inches, that will give you the FO max. Again, FO max will be the maximum fluid loads that the pump will be capable to lift, assuming that you have no lifting from the well.
Super, thank you. Okay, the next question is, this customer opened up their version of TAM and they're using 1.7.41, and they just made the comment that they don't see the power torque tab.
Correct. That's because he didn't acquire power data. And I'm going to pick another session, and let me see if I have one here without power data. Probably this one. Probably all of these wells will have, all of them will have. But let me select just a different well. I'm going to jump to this other well, the dynamometer and the raw data. And this is what he's very likely looking at. His software doesn't have any power data on it or power torque, because it's not being acquired. It's just acquired dynamometer data with this sensor here. So if you go to the test information, you were using only in this case an HT. You probably use a horseshoe load cell like this one or a PRT, but no power probe like in that other well.
Perfect, thank you. Now while you've got the TAM software up, we have a question about the raw data tab. And Milena is asking, what does the data look like if you have an issue with the valve? What can you see when you're looking at the raw data?
Okay, on the raw data first, let's on this well. Like on this well here, we're looking at the raw data, and this is the whole raw data, probably a little bit confusing, but if we focus in a smaller part, like by looking at just the raw data, you can see how the peak-to-peak loads has changed at this point. So something happened here. You can also, if this data set would have a valve test analysis, that would be available here to double click on it. So you can access the valve analysis from the raw data. I'm going to jump back to that well, and I'll be back in this one in a minute. So that was the V11, and I'm not sure if I have that's label level. So like this is the raw data, and the raw data you can see how many plots, how many strokes you have. That's one thing, and you can see how accurate the software is doing a proper job on selecting the strokes. And also you have the valve analysis, so you can double click from the raw data into the valve analysis module. I hope that answered the question. Is that okay?
Yes, that's great. Thank you. And then Milena had a follow-up question. What is the recommended efficiency for the system analysis?
It's well, as big as you can have it. It's not what we will recommend for the efficiency, because you cannot input that. You need to properly size your system and run your system in a way that it works in the most efficient way possible. So you don't want to over-dimension your pumping unit, your motor, your pump, so you have a partially full pump. So you want to have a power transmission from surface to bottom that is actually used for lifting fluids and not having so much, hopefully not having so much friction in the system, or not having so over-dimensioned components in the system that can lead to a very low system efficiency. So as high as you can, but usually what I would say over 50% would be okay for a rod pump system. A rod pump system will be a much more efficient system than many others. Like if you compare that to a gas lift, rod pump will be way more efficient than a gas lift. I hope that answered the questions.
All right, and then we have another question about power data. And the question is asking, how does software calculate power at the polished rod and the pump?
Okay, let me open this one here that we work related with. So the power in HP will be calculated based on the area at the surface car. That we're talking about the polished rod power, and I think we use a trapezoid calculation to estimate the area. And power is just to put it in simple words, we're lifting so much weight for what's the stroke here, 100 inches. So we're lifting 100 inches up and down, this much weight in certain time. So we're moving a body with a mass, certain distance at certain speed or during some seconds. So that's converted into power. So time, weight, and distance is converted into power. Now, Lena, we can discuss further on. I can show you some examples on how do we calculate the power either from the surface or downhole car. It's exactly the same calculation, but it has to do with the dynamometer card area inside the car. Like if you have a flat dynamometer card in a parted rod, the plunger is not lifting any weight. So the flat dynamometer card means there is no power being lifted by the pump. Or when you have a plumping well, you have a very flat dyno car, which means the pump is doing almost no job at all, and that will result in a very, very low pump power. And we can further discuss about it.
Okay, and then just one more comment, really. When you have several dynamometer cards overlaid, how would you know which color card is for which date once that overlay section tab is closed? And then Dr. Podio commented you would need to put notes on the dynamometer window. You'd be able to label those.
Correct. That's a good point. Let me go to the when we were overlaying the strokes. There. So how do we know which color card belongs to each specific date? Well, when you open it, you know it, but that's right. Once you close this window, you won't know which one it is. Then you can do what Dr. Porter said. You can put comments on it, and let's do that real quick in the software. So let's go to Annotations and Previous Strokes. I'm just going to pick other two. I need to be in the field view, by the way. And let's find one with, okay, that one was okay. This is pretty much the same. This is the same, so they're not being overloaded. So like this light blue would be, let me put it better, that would be 8:56 a.m. So we can put a comment or add a note and say 8:56 if they were the same day. So that would be that dynamometer car, and you can also do a comment on the next one and so on. That's how you would. It's a good observation. Thank you.
All right, great. Thank you, Gustavo. That's it for the questions and comments right now. So please feel free to pull up those great TAM examples that you have.
Okay, let's work on that. I'm just kind of putting the comments on this dynamometer car. So this, the black one would be the current car. This would be this date and time, and you can just label them. Okay, let's review some examples here I have for you where we can use these features and see how we can benefit from those features in the software. So let's go to pick a well. The first well I'm going to check is an anchor. This well is in the examples folder, and this looks like a regular dynamometer car. We can actually let's try to use what we have learned today, and we can see something here. And one of the reasons I like to plot the two dynamometer cars in the same plot is if I have that, well, I have the sense like I have a full plunger stroke. The pump stroke is very similar to the surface stroke, which is might be wrong. Like this one here is almost 86 inches, and down there is only 59 inches. So when we plot both in the same chart, we put surface and downhole in the same plot, so we see how much rod stretch we're having in this stroke. That's one thing. So another thing that I want to show is a event. So it looks like we're having a full pump, but if we review this well, actually the well was coming with a really pumped off condition. And one of the benefits that you can have by acquiring continuous dynamometer data is you can catch these kind of behaviors in the wells. Like if you do it if you collect one dynamometer card from a PRC, that will be one single card. You won't be able to see the difference. Of course, we were lucky to catch the behavior in this well. And when you're troubleshooting well, you probably need to spend more time on it. So probably if you just stick to this idea, you would say, well, my well should be producing a lot more than what it is. So I should be getting like 84 barrels a day, but I'm just getting 50. So what's going on in the well? Well, the pump is not being full all the time. When you analyze the well and you see a lot of dynamometer cards being very, very low pump fillage. So this well has a kind of a strange behavior. The pump is not being full all the time. So by using the events, you can scroll and analyze. So let's stick to the full pump. Let's focus on that full pump. And another thing that you can see is, it looks like I'm having a lot of rod stretch. On the analysis plot, that can be visualized. You can see, if you look at the left-hand side, we can do this in different ways. We can do a replay, and we can have the last strokes, like from 97 to 99. I will update that and play that movie. And you will see how the plunger stays almost stationary at this point, and I will stop that. And see, on the surface plot, we have the polished rod position against the on the plunger position, and we can drag this cursor moving up, and we see the plunger has moved only 3 inches, while the polished rod 47 inches. Let's combine these two as we have the same unit. So the plunger is pretty much steady, and the rod is stretching up. And we can see also, if you look at the left-hand side, you see the polished rod moving up, and the plunger is barely moving, and stretching the rods until finally the rod stretch is completed, and the plunger takes off and goes up. And on the bottom screen, we have the plunger velocity. So the plunger velocity is really close to zero during all this area. Okay, and then suddenly the plunger, boom, increases the speed really fast, and then once it reaches the top and at the upstroke, now the rod shrinks, and we will see how the polished rod is moving down while the plunger is waiting for the rod shrinks. It's barely not moving, and the position again is the same, but the velocity, you see how the plunger is pretty much stopped. It's the zero inches per second, so it's not moving. It's not moving until all the shrinkage happens, and then the plunger takes down, and we see the negative plunger velocity being kind of high. So this is kind of a useful analysis to understand when that or how that rod stretch is happening, the behavior of that. Let's check a different well. We have another well here. How is our time? We're still good. This well here, I think we had a question about the traveling valve. I think was Milena asking something about the traveling valve. So in this well, if we look at only the traveling valve, we see, well, the traveling valve is just dropping. Well, let's wait and review this analysis a little bit better. We of course have to activate the plots, but we see something. Hey, I have no strokes on this one, but that's fine. This is a valve analysis. And if we stay here, we say, well, this is the plunger stop, and there is not much pump, there's not much loads changes until this point. The loads drop, and we can see how we have to wait kind of almost more than a minute here to see the loads dropping. So it means that the plunger, the barrel wasn't full, and there was slippage happening, and at this point the pump was completely full, and this happened. That's one of the things. On the other hand, looking at the loads drop doesn't necessarily mean that we have a traveling valve leakage. That's probably the general assumption. If the valve is leaking, the loads will drop. Yes, but in this case, the loads are dropping, but we also have to consider how bad are they leaking? Although this only represents 0.25 barrels a day, that's almost nothing. So this may be just the natural pump slippage. So it's just a regular slippage that's actually necessary to lubricate the plunger in the pump. And all the pumps will have some leakage. All the pump will drop the loads when you stop them. So how fast those loads drop is important. And this window here is actually a 15 seconds window. Probably we're showing up here a very long tray. So what we can close this out and see another area, and let's focus on this one here. So it's actually, you can modify the points where the software calculates the load drop and how wide the interval is. But anyway, no matter where you put it, it will be a very low uh, leakage, or in this case, not leakage, actually slippage. But coming to the dynamometer section, so the next or the previous acquisition, this is a separate acquisition, purely dynamometer and purely a valve test. So we see again the software didn't perform any stroke calculation, so it wasn't able to find any stroke. So in these cases, we need to reprocess the data. If that's the case, we're going to click on reprocess, and we're going to change to histogram, for example, and try to reprocess. It will ask us if we want to continue with the processing, and we'll say yes. And there's a warning here, kind of a warning. The software is telling us, well, according to your input, the stroke length is 85.7, but what I'm calculating based on the acceleration data is 68.38 inches. So what is the right thing? So you need to let the software know what is correct. Probably you have a wrong input in the well file, and you need to check that in the unit. So either by the crank hole that is being there, or if you have a hydraulic pumping unit, you can measure the stroke length with the measuring tape. The software will show this when it finds more than 10% difference between the input and the acceleration from the stroke length calculated from the acceleration data. So I will assume that 55.7 inches is correct. I will say OK. And the software now calculated only one stroke. Well, that wasn't that good. So if I look at all the QC tray, the dynamometer data, only one stroke was calculated. So that method didn't work pretty good. So I will change the classic method before I change the filter. So there is not a fixed rule that you need to try some kind of combinations, different filter width like 0.5, 1, 4.11, and usually those three give us the best results. But on this one, let me try with the classic method. And again, the software is calculating something different. I will stick to, I know for a fact because I measured that in the unit that 85.7 is the actual stroke length. And voila, now we have all the strokes calculated at 24 strokes. It's the same data set, we're just reprocessing it. Let's look at the data inside. And right now we have the number 24 selected. So if we click on details on field view, we will have the stroke number 24 being plotted. And the first one wasn't good. And let's see if we select another dyno car. Well, this wasn't the best method. And we'll click on event. And we'll see some data is not properly calculated. So let's try it one more time on reprocessing. And we can do that several times and iterate until we find good results. And I'm going to try with the low pass filter. Again, 87.5. And probably now it's good. And we see better dyno car shapes. And let's click on there and see, well, not this is good now. So we needed to iterate a little bit with the options that we have in the software in order to get a good downhole car calculation. Well, actually, it's the position calculation what is being affected here. So this dynamometer car, as we assumed, we have a partially full pump. This is not full. It's 75%. So in the valve test, we don't have any valve test here from this raw data. So we need to check the valve test. And clicking in here, we'll see this is the new software analysis. We saw the pump stops and it's leaking a little bit from above the traveling valve. down to the barrel, filling the barrel. Once the barrel is full, now the loads drop. So, but in this case, we need to wait a little bit more.
Let's see another example. And this other well will be heating up. The pump is heating up, and this is the valve test, and this is the dyno card. This well, I had the chance to measure it back in 2007. And if we look at the dynamometer card, we have a quick load increase at the very end of the upstroke. But based on what I observed at surface, I'd assume something different. So at the rod coupling, the polish rod coupling on top of the polish rod was actually touching or tagging on the horse head at the very end of the upstroke. So when I was expecting to see that in the dynamometer card, because we installed a horseshoe load tail and we didn't have a PRT with us. So in order to measure the dynamometer card, we installed a horseshoe load tail. And one of the cons of using a horseshoe load tail is in order to install it, we need to respace the pump. Actually, we lift the polish rod about 3 inches with the horseshoe load tail installed, and as a consequence, the pump is spaced up. But aside that, when that happened, the polish rod safety coupling was touching the horse head at the very end of the upstroke. So I was expecting to see a load increase uh, right there. So when I was measuring the dyno car, I was observing this spike. I said, well, that's a surface condition. But it wasn't right, so it was a wrong assumption. If we look at with more details the data, and we see the spike or the load increase at the end of the upstroke, but if we focus on the slope on the rod shrinkage during the downstroke, and we need to plot something else here in the annotations. We're going to plot the rod tubing stretch. And the rod tubing stretch is this value here. It will be showing and now a new line in the surface card. You see there. And what the slope is telling us is we need 393 pounds to stretch the full rod stream 1 inch. So that's basically what that line is telling us. So if we look at that slope, that's very similar to this one. So we cannot move it here. So what I did is I took that information into just copy the image and paste it in PowerPoint and draw a line just with the same slope that the KRKT. And if we put that over here, so if we overlay that, we see how the slope matches almost perfect on the rod shrinkage during the downstroke. So this is confirming that actually the rod was stretching from the pump. So the pump was actually tagging up, and we can confirm that by looking at this. So, or what you should do is actually plot the information, export that into Excel and plot it, and have the drawing with the 393 pounds per inch slope, and this is pretty much the same. So it is actually matching very, very good. It is confirming us that the rods are stretching from the pump itself. So it's a full rod string stretching and shrinking here. What if we look at that from the analysis plot? So on the analysis plot, let's remember we can plot several values. And what I have right now here is the polish rod position compared to the polish rod load. So we drag the line, and we will take this to the point where the loads increase. It's right there. So this on the bottom chart, I have plotted the surface dyno car. So that will be the polish rod load against the polish rod position. That's the surface car. So at the point where the loads increase, we have 2.7, and we can change this. Usually it's in clock, but it's better for us to analyze right now this example in seconds. So at 2 seconds from the beginning of the stroke, we have an increase in load. This is just the spike. Then we have a second spike at another load increase at 3.1, and that's 0.4 seconds. And the 0.4 seconds this is a 3,300 feet deep pump. So usually the sound wave in the steel is about 16,000 feet per second, which matches with what, about 0.4 seconds. So this is a very likely, this is a repeat of that spike and a round trip travel time on the rod string. So this is also kind of confirming that we have a pump tagging down. So we can see or observe a wave traveling across the full rod string. So how we know that is we can calculate 33, 30, which is the pump depth, and the wave will need to have a round trip travel time, which is times two divided by approximate the sound speed in the steel. So that's 16,000 feet per second. That's 0.4 seconds. So that's pretty much what I'm looking at the difference. So 3.1 second minus 2.7 seconds, that's about 0.4 seconds. So that's a kind of a confirmation together with the slope, and the slope is the most representative information we have. So from here, plotting the KRKT, looking at the slope and how the loads changes is a confirmation that the pump is actually tagging down aside what I can observe or see or listen at the surface. This is a very good example. So before going to the next well, I will need to select this. Picking the next well will be this one here, stock plunger.
So this well, if you look at the dynamometer car shape, we say, well, what's going on here? Important thing is we have, right now, we have plotted in the annotations, we have the first option here, rod tubing stretch on surface car. And without this line, we probably wouldn't know what's going on right now. And we're plotting separately the surface and downhole car. So by having the rod and tubing stretch in the surface car, we see how the dynamometer car kind of follows all the way up the same slope than the rod tubing stretch line. So this means this is just stretch. This is nothing but stretch. Look at the surface stroke, and the surface stroke is 120 inches according to the pumping unit, but the bottom stroke is much lower. It's only is less than 50 inches. So I'm going to show the surface and downhole car in the same plot, and we'll say, oh, wait, now it makes sense. Now we see a very low plunger movement compared to the polish rod movement. And if you look at that in the analysis plot data, this is a hydraulic pumping unit, and we see how the polish rod position is kind of linear going up and down. It's much slower going up and much faster going down. It takes less time to decrease the position. And we can plot that against the plunger position, for example. And let's combine this, and we'll see how the plunger is not moving, and after, well, almost at the end of the stroke, the plunger take off, moves out. But this is just the stock plungers, and it's really clear when you see the surface car slope just matching almost exactly with the rod tubing stretch line. And the events, if you open the events, we won't tell you much. It's about the same dyno car every time. We didn't see any car where the plunger actually doesn't go through this sticking point. Next well, let's talk about the damping factor. This is a well has a fairly good pump submergency. We can see that here. On the pump car, I'm going to switch into the dyno car. So these are the dyno cars, and we're looking at something here. If we focus on those FO line, FO max and FO from fluid level. So according to this right now, the dynamometer card is kind of matching the FO max. If that's the case, the fluid level should be at the pumping tank because the pump is lifting all the fluid weight. And when we look at the fluid level, we say, well, that's not the case. We have a lot of pump submergency. We have 3,700 feet of pump submergency with almost no gas being produced. Well, this kind of round shape on the dynamometer car we see in the events is not just not regular shape. It's kind of rounded because this is a high viscose oil. So on these kind of cases, we'll say, well, I know the system has a lot of friction. This is heavy oil well, and I will click on uh, pump car analysis, and the first tab would be the damping factor. And the damping factor, we'll need to adjust that. And we say, well, let's move this up, or let me unlock this. And I will put this to probably this a little bit more, 2.36, and I've been doing this before, so I know kind of 0.36 helps me to have a more decent dyno car. Well, this is a more rectangular dyno car. Surface loads or upstroke loads actually are kind of matching with the FO, and this is a more representative dynamometer car for this condition. So we know under high viscose oil, this is like 12, 14 API, creating a lot of friction in the system that the wave equation is not accounting for. So we need to alter the damping factors, and we were using zero 0.2 and 0.36 in order to bring a better dynamometer car shape, a more representative one. The more viscous and the more deviated the well, the more rounded it usually looks. Event shows about the same. I have another well that has event. This is a for a full pump, but this one is a incomplete pump pillage. And even though we have almost 800 feet of pump submergency, we see something at the pump. So this is kind of the oval shape that I was mentioning before. And this is a 10 API degrees oil in this well. And well, this shape here, for the people who's familiar with heavy oil, we say, well, yes, I have a very likely fluid pound. If we review the fluid level shots, this well produces almost no gas, and that's very common in heavy oil wells. So this incomplete pump failure is not due to a gas interference, but it's not a pump off well. So we call this as a fluid pound due to viscous oil. So it's just too viscous to fill the barrel fast enough while the plunger goes up. Well, but even though by keeping the FO max line there, the upstroke loads are actually like double that load, so that's impossible. So it's telling us there's a huge amount of friction in this system. And again, we'll need to go to the damping factor and bring those values to a better place until I think 0.28 will work for this. I've been doing that before. No, 52 point. You see how the dynamometer car shape, if you look at here or here in the plot, dynamometer car shape adjusts right there. This is a much more representative dynamometer car shape. So we checked the plunger size, we correct the fluid level information, almost no gas, so the liquid level information may be accurate because the tubing gradient is related to fluids. So this is a much more reliable dynamometer card. So we decreased like several thousand pounds the downhole car calculation. So the damping factor again, unless you are under high friction systems, you usually don't need to modify the damping factors. And you need to be careful on that. I'm going to just play with it a little bit. So we can have crazy things if you just start to play with the damping factors. You just got to be careful with that. I'm going to bring it back to the proper place. So 52, I think, is okay. If you're going to work with the wells later on, I think I have placed some comments. If you click on edit, some of the wells have what do you need to do in order to get the good dyno car shape. Checking this one. Like this previous well, there's a 10 API, and adjusting the damping factors to 0.28 up and down will match kind of the expected pump loads. Okay, I have just a couple of more wells to show you. Let's see here. There's a slow SPM, and again, opening the data file, no strokes being recorded. This is the one that I showed you before. Coming here to the histogram and moving average filter, we will have now was 22 pump cards, and this is a high friction well again. This is really high, and the previous well was like 1.3. And the first thing we need to notice here, well, the traveling valve point is not correct. So to look at the traveling valve point would be here. When we do that, we'll see that there is a higher load and a much lower load here. So this is a high friction well again. So we'll need to go to adjust the damping factor to correct the height at the pump car. So I guess it's a fluid pound condition, very likely due to the viscose oil. And there is one more well. This other well, this is the last well I want to show you today. The gentleman will say, "Hey, Gustavo, what's wrong with my pump?" I said, "Well, I don't know. Send me the data and let's see." He was trying kind of describing the car shape, which I don't know how to do that. I said, "Well, let's see first." And the first thing that I was doing is let's check on the events to see how the rest of dyno cars look. And look how the first dyno car looks, and see how it's sloping down, it's tilted down. And the stroke length calculated was like 54 inches. If you look at here on the events line, we see many of the dyno cars are tilting down, but then they start getting straight, and these are kind of normal cars, or let's say at least horizontal flat. This is at least the upstroke loads are looking better. And then the well kept running, and now the dynamometer cars are sloping up. I said, well, let me overlay this. I'm going to keep that one. I'm going to take one of the kind of the horizontal ones and the first one. So I have three completely different dynamometer cards here. So this doesn't make any sense. This is a normal behavior for a well that is first being measured with a PRT. So this is a polished rod transducer measuring a well that has a bent polished rod and a rod rotator. So I call the guy, "Hey, you have a rod rotator running in this well." "Yes, how do you know?" "Well, because the slope is changing." But aside that, I'm going to reprocess the data. Let's just select the first dyno car. Anyone would be okay. So I'm going to raw data. I need to reprocess this. I will see if something changes there in the car shape. And I will just keep the default in the software and click on reprocess. I will say, yes, I want to reprocess the data. But now, boom, the software is telling me this. Well, the entry stroke length is 57 inches, but the calculated by the acceleration is 86. So, well, what type of unit you have? When checking the pumping unit, I see the maximum stroke length of that pumping unit is 86 inches. So, well, let me try with 86 inches to see what happens. And suddenly, that car shape now becomes in this, but I'm going to again see this. These strokes are tilting up, and then we see some like normal cars, and this looks much better. And the first one are tilting down. So, well, I think I'm going to get kind of the right point, and I guess 22 is a good average. It's a good horizontal dynamometer car. So this is a series of problems going on here. So first is it has a surface condition that is not appropriated for the measurements. It has a PRT measuring and bent polish rod and a roll rotator. And I'm glad that he had the roll rotator because he had the slope tilting down, horizontal tilting up, and this is normal because the bending of the polish rod is changing position. And the cross-sectional area where the PRT is measuring is changing while the polish rod is rotating, and this would be the representative car. But let's assume he didn't have a rod rotator there, so we only have this dynamometer car. Look at the stroke length in the stroke number 22, which is kind of a normal dynamometer car. It's close to 62 inches. Okay, assume he only had a couple of dynamometer cars. This stroke length was wrong. I mean, the downhole stroke was 80 strokes, 80 inches. So we're going to use a pump car analysis and D-ramp, and we're going to turn on the D-ramp. And we know that goes now from 80 to 62.7 inches. So the software is actually not only straightening the dynamometer car, but it's also correcting the bottom stroke of the car, or the pump stroke, to almost exactly the same what we had in the horizontal car. So this 67, I'm going to turn it off, is very similar to the dyno car number 22. So even if you have a tilted dynamometer car, when you record with a PRT, if you turn on the D-ramp option, it will fix it for you. And that was the last well I had. Let's see if we have some more questions.
If you guys have any questions right now, we'll give you just a minute here to type them in. We've got a few minutes left. And when we show you guys TAM examples, we really encourage you to go out to the website, download the TAM examples. You know, we have the recorded sessions available for you to watch later, and lots of times it just really helps to pull up the data with us, go through all of the analysis steps with us, you know, kind of get used to using some of the other tools. That'll really help you get a good method of analyzing your data and understanding what to look for and finding some new things. Well, I'm not seeing any more questions come across, Gustavo.
Okay, well, just to let you know, if you open the edit button where you input the well information, on the last tab, well description, most of the wells, I try to do for all the wells, probably not. I put some comments on kind of what's wrong with the well or what you can try in order to get it fixed. So like this one is a stroke length input 56, is the minimum stroke length for that well. If we check the lift system, that's 56, 86, that's a minimum stroke, and 86, which is pretty close what the acceleration calculated, is the maximum stroke length. So I kept it with the run information so you can go and process the data by yourself. So the correct one is the 86 maximum stroke. This is a polish rod is bent and acquiring data with the PRT. The dynamometer car 22 is used as a representative one. Anyway, it's a rotator installed and working. It's kind of some few comments for you to have a guidance on the analysis.
All right. Well, thank you so much, Gustavo. That was a great session, great demonstration. And to all of you joining, we hope you enjoyed today's session, that you learned something new. In the event you do have any follow-up questions, we always welcome your calls and emails. Next week's session, the focus is going to be on gas separators and gas separation techniques. We also have a cool little gas separator simulator that's free for you to use and download, and so we'll talk about that. If you're on the registration list for the weekly sessions, you'll automatically receive a link to next week's session. Otherwise, feel free to go to our Ask Echometer webpage. I just posted the link on the chat. You can register there. You can look at the previous sessions that we have. Gustavo mentioned several of them during his presentation today. And we'd just like to thank you guys for joining us and for the great questions and your comments. We appreciate your time, and we're so glad you joined us today. We look forward to seeing you all again next Wednesday. So thank you so much, and we hope you have a great week.
Thank you.